Okay, so welcome to this video overview of life cycle of a star. There are lots and lots of videos on, and some very good ones. I'll put a link into some others that I like for life cycle of a star. The reason I've decided to do one for you in particular is because I think there's not many that are just focused on what you want to do, the key terminology for GCSE, and particularly the syllabus you're doing. So let me go through this one. Please watch others as well, because I'll fill in some of the other gaps and just to give you a more rounded knowledge of it. So I'm going to very much focus on what would be a good answer for particular stages in life cycle of a star. So let's start off. If you want to get a decent mark, you need to know the key terminology, the key phrases for this. So we'll just start off giving a very quick overview. Where do life cycles of a star start off? Well, they start off with nebula. Stars are born in nebula, and nebula is really just another word for space dust. So that's really the first stage. Space dust eventually comes together under a force of its own gravity, can take billions of years. And when something's on the way to becoming a star, we call it a protostar. So, but a protostar is not yet a star because there is not this magical process. Well, it's not magic really, is it? But there is not this process going on which is called fusion. And fusion is really when we say the beginning of a star. And the proper name for what is a normal star in its main part of its life cycle is it's called a main sequence star. So our sun is about 4.5 billion years as a main sequence star, and probably got another 4.5 billion years to go approximately. So that's what this main sequence star. We'll talk about what those arrows are mean in this diagram a bit later. So eventually a star seems to run out of fuel because it's fused its hydrogen to helium, and maybe it stops there and it can't carry on going. And that's generally the path that smaller stars take, like our star. Even though our star is not a tiny star, it's not a tiny star compared to others, but it's not the largest star. It's not one of the supermassive stars. And eventually our star will run out of fuel for this fusion process, and it will start to collapse in on itself. As it collapses in on itself, the outer layers expand and it starts to cool. The outer layers cool down, and so it takes more of a reddish tinge and it actually expands out. But and the reason is because it's actually the core is getting more dense and just has no fuel left, so it just collapses in on itself. Eventually then, after a long time, the outer layers spread out and you're just left with the core of the old star. Now, this is not a biological term, but in the middle of the star, it's now something what we might say is dead, i.e. there is no fusion going on. It's really just a big, hot remnant of the center of the old star. No more fusion going on, and it's called a white dwarf. Now, after a very long time, a white dwarf will cool, and it will turn into a black dwarf. There's no actual black dwarfs in the universe at the moment because the universe is not old enough for a star to have gone through that life cycle. Now, if we start to go through a larger star, we'll go through exactly the same process up to main sequence star. But when the larger stars expand, they actually have a different name. They're still red giants, but they're red supergiants. They're just bigger giants. And what fundamentally happens here is the big change, because what happens is they just get bigger and bigger, and then eventually they just collapse in on themselves, so they run out of fuel, and they then explode in what's called a supernova. Now, once a supernova has blown up, and that is one of the most powerful events in the universe, we will be left with one of two things. We'll either be left with a neutron star, which is just a very dense piece of matter and spinning very fast in space, or if it's very massive and it's got enough mass, then it might turn into a black hole. And a black hole is something that's got so much mass and so densely accumulated that mass that even light cannot escape from it. Okay, so if you look fill in your diagram on the sheet here, I'll put a link into the onto the YouTube video as well, so you can access this sheet if you haven't got it from me in class. So let's just spend a little time going through the details of what would be good answers in these boxes. So I'm going to start off with a main sequence star, how it's formed, and then go down the smaller pathway, and then we'll go on to the larger pathway. So fundamentally then, what are we looking at here? This is this box. Explain how a main sequence star is formed. Well, as we started off, a main sequence star starts off as a cloud of space dust called a nebula, and eventually gravity will pull that space dust together. Now that could take millions of years, but it will eventually. And obviously, once any two clumps are together, then they'll have more gravity than just one the clumps together, and the process will sort of start to accelerate. The energy changes involved here are really when all these things are all these pieces of dust are spread out, they have a lot of GPE, gravitational potential energy, because they're far apart, and as they come together they will gain kinetic energy. And as all these dust particles eventually come together and start to coalesce and spin around each other, they'll start to rub on each other and generate lots of heat. If we're on the way to becoming a star, if we look at a cloud of dust, hot clouds of dust in the sky, and we see that it's coming together, and we know it's going to come on to become a star, that's where we use the name protostar. So it's something that's on its way to becoming a star, but hasn't quite got there. Now, very important stage here. This is main sequence star. I suppose in effect this is when the lights come on. And what I've drawn here, so here's MSS, stands for main sequence star, and what is the process that powers the star called? It's called fusion. And that is really what's going on in this diagram up here. It's too large there. Let's get that smaller. This is what's going on here. This is fusion, and it's simple terms. This is fusion. This is a hydrogen. This is a proton and a neutron. This is a proton and two neutrons. And really fundamentally, because in stars they are so hot, there's so much kinetic energy, they're so dense that this unusual thing can happen, that two nuclei can be smashed together because of extreme high pressures and temperatures to form a different nuclei. So this doesn't really happen. We sort of can just about do this on the Earth, but we can't do it in a controlled manner. So there are no economic fusion reactors. We have fission reactors that split things apart, nuclei apart, but we can't do this. Now the reason this particularly, so where does the energy come from? The energy comes from nuclear fusion. And what is the fuel? Well, fundamentally, what's going on here is that the mass at the start and the mass at the end is not the same. Even though there are 5 nucleons here, that's got a relative mass of 5, and 5 nucleons here, that's got a relative mass of 5 as well together. The actual mass, if you measure it very accurately, is slightly different. And actually that mass difference has been turned into energy according to Einstein's formula, E equals mc squared. Now c, if you remember, is 3 times 10 to the 8. So 3 times 10 to the 8 is 9 times 10 to the 16. So each kilogram of mass that you manage to turn into energy generates you 9 times 10 to the 16 joules of energy. So it's quite a lot. Okay, so that is where the energy of a star comes from. So next thing, what is the force that makes a star want to expand? What is the force that makes it want to collapse inwards? Well, the force that wants it to expand, if you think of all this energy being created, then you're having an outward expansion. All that energy wants to make the star get bigger. So sometimes we can call that fusion pressure. So you could label these outward arrows fusion pressure. What is the force that makes the star want to collapse inwards? Well, that's fundamentally the gravity. Now, which is bigger? Well, our sun has been around for 4.5 billion years and is likely to be around for another 4.5 billion years. So that might give you some indication of what those forces are like. These forces are actually balanced. And the reason they must be balanced is because to some extent they're in a negative feedback loop, and that sort of means they just sort each other out. For some reason, if the gravity just seemed to increase magically for some moment, and the star started to collapse, well, that collapse would also cause the pressure to increase in the center of the star, which would mean the fusion would have to go up, and eventually the fusion would go up. The more the gravity increased, the more the fusion would go up to eventually match it. If you think for another reason, if for some reason the gravity just sort of went weaker for a moment, and the fusion stayed the same rate, well, the star would expand outwards, and that would mean the density and the pressure and the temperature in the middle would go down, which means the fusion would go down. So it's no coincidence that our local star, the Sun, is stable, because these two forces, while there's energy, hydrogen, to fuse into helium, then these two forces must remain the same. So there you go. How long will our sun stay for? For another 4.5 billion years. Okay, what's going to happen to our sun in another 4.5 billion years? Well, if I just go back to here to this, let's get rid of those annotations. I go on to eventually we're going to run out of hydrogen. And when we start to run out of hydrogen, fundamentally we're running out of fuel to power the star. And when we run out of the hydrogen, maybe we'll start to fuse helium to slightly small things, but small stars eventually just run out of materials that they can fuse together because they're not hot and dense enough in the middle. And as they start to run out of material to fuse, the outer layers disappear off and cool down. And that's called a red giant. Eventually, most of the inner planets in our solar system will be consumed by the sun, because the sun will just expand to very large. It will actually be slightly cooler. There'll still be thousands of degrees on the surface, and it will just destroy all the inner planets. So this is when the fusion process ended, no fusion occurring. So what's going on? We then move on to the stage called a white dwarf. And a white dwarf is fundamentally maybe something the size of a typical planet, but it's just the remnants of an old star. So there are white dwarfs around. They're very bright, they're very hot, they're very dense, and there's nothing going on in the middle of them. So they will eventually just cool down and become black dwarfs. Now they take so long to cool down that there are actually no black dwarfs in the planet in the universe at the moment, because for a white dwarf to turn into a black dwarf would take more than the age of the universe at the moment. So let's just go back then. So we've done this side now, which is the smaller stars, or stars approximately the size of the sun. So I'm going to focus on the other side now. So we've already gone through the name of these points. Really, and we've already covered this point, because the nebula to protostar to main sequence star cycle is exactly the same for our larger star. The only difference becomes after this section, where the other one would have gone to a red giant, and this one is going to become a red super giant. So let's try and explain what's going on here. Well, we know that when a main sequence star comes to the end of its life, well, we know that when a smaller star comes to the end of its main sequence stage, that hydrogen is running out of hydrogen to fundamentally turn into helium, and that's why it runs out of fuel, and it doesn't have enough mass to actually cause enough pressure and temperature in the middle of the star for this to carry on. However, in larger stars, and you can see in the periodic table here, then hydrogen, there is no problem turning hydrogen into helium, and in fact the helium can actually be moved on to become lithium, and the lithium gets turned on to become beryllium, and the beryllium can be moved on to be turned into boron. Now every time this happens, really it becomes a little bit more difficult, because the nucleus becomes more positive. When you squeeze the protons and neutrons together, well, to get larger elements you need more protons. So as the proton number increases, the positive charge of the nucleus goes up. which means that you need more pressure and temperature. So every time the star starts running out of fuel, because there's only a limited amount of fuel inside the star, it undergoes collapse. And that collapse goes on until it gets to the next stage. And when that next stage goes on, the fusion, the outward pressure kicks in again and stops the star from collapsing. And that can sort of happen on the other path, all the way up to typically up to something like carbon. And once that path is over, because you can't squeeze the carbon together to make anything bigger, because there's not enough energy, because there's not enough mass, well, that's when you would have gone down to the white dwarf stage. However, in larger stars, the process carries on, and carbon gets made into nitrogen, and then oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium, silicon, or Ti, titanium, vanadium, chromium, magnesium, and then we get to this really important one, iron. And when you get to iron, you cannot fuse iron together. And that's because when you're trying to go up here, you need to put energy in. So when you're trying to make these elements, you actually get, if you take large elements and you split them apart, you will actually get energy. So to get iron to be made into bigger elements, you need to add energy in. Now the effect of this means here that really all we now have is gravity pushing in, because you actually come to a point where there now is no fusion pressure going on inside, and the star really just can't cope anymore because there's no fusion, there's no fuel to power it, and the star just collapses in on itself. And this is really known as a supernova. So the key point is that you get more stages of fusion on this side of the cycle. Because you have a bigger star, you can make bigger and bigger elements, but eventually you hit a brick wall, and the brick wall is really iron. When you get to iron, there's no fusion goes on. So you get this massive collapse of gravity causing the star to collapse, and then it explodes and rebounds on itself, and this is called a supernova. And in this instant, this is when all the elements that are above atomic number 26, which is iron, in the universe are made. It's the only time. So if you ever come across an element, so there's lots of them in your body, there are, they're essential for life. Some of these elements like nickel and zinc, and magnesium, they are essential for life, and they're all higher than atomic number 26. Oh no, not magnesium, sorry. Magnesium is 12, but there are lots of others. There are lots of elements above in the periodic table, and they are essential for life. So they're in your body. So parts of your body were inside these supernova events. Okay. So what goes on after a supernova? Well, a supernova, I suppose, is the end of the life cycle of a star. All that stuff gets sprayed out, and somehow, in some ways, that can be the beginning of other stars. All the stuff that gets sprayed out by a supernova can at another time go on to create new stars. That space dust gets spread out to space and can then form again. So what do we have left over? Well, there's two options here. There's one, this is called a neutron star. A neutron star is really something so dense that all the electrons have been squeezed back into the protons to make neutrons. So there's only neutrons around. It's almost like just a large nucleus. It's just a massive, massive, massive nucleus made out of only neutrons. It's super, super dense. If you remember back to the atomic structure unit, I was talking about the difference between the size of the atom and the size of the nucleus, and talking about the majority of the atom being empty space. Well, all that space has now disappeared, and all the neutrons are just banged in together. Right together. So it's much, much, much denser than normal matter. Now, unusually, if there is enough mass left around, then we can find ourselves with enough mass that not even light can escape. Because if objects need to travel at a certain speed to escape gravity. and if this escape speed that they need to get away from the gravitational pull of an object is greater than the speed of light, then that means light can't even escape that object. So those objects just appear black. And that object is known as a black hole. Now, guys, so hopefully I'm trying to fill in as much detail as possible for the sort of typical exam questions. There are lots of other good videos. There's not, there are lots and lots of videos about life cycle of a star. Some go into more detail than others. I particularly like this one, which is the Institute of Physics, so I'll put a link to that one in my YouTube as well. So hopefully look at either one that supports your learning, but really the key idea is trying to get some nice good key ideas into these different stages of the star. So if you can complete that and if you want to get some model answers off me, then email me and I will send them to you. Okay, thank you, goodbye.